currently an applied scientist in Wave, London, and his research interest is on the autonomous and self-drive. In the large language model to the self-driving reinforcement learning. And he previously worked in San Diego as a vice president of the research development, and he led the research effort in scalable robotics. And let's welcome.
Okay, hello, my name is Oleg. So yeah, this is actually a new presentation. It's all going to be multimodal and trustworthy, if you guys want. So I'm from company Wave, and Wave is a self-driving startup in London. And what we're doing is making cars autonomous. And the main idea of the company is to differentiate ourselves from a previous way to do self-driving, which appeared from DARPA challenge, which is called AV 1.0, which consists of taking data from sensors and going from many perception modules like lane detection, traffic light detection, and so on. Then you have explicit planning module that can predict things, that can perform different trajectory planning, behavior planning in optimization, symbolic way, and so on, and control. And instead of that, replace the whole system in the middle by a huge neural network, end-to-end, which just takes camera inputs and some other inputs like GPS and so on, and learns end-to-end to control a car. Obviously, there are some other components like actual controller and safety purification system, right? But the main logic of all those components is just the big neural network. And the reason for that is that there are several very nice promises of such end-to-end systems that recently, started to kick in, and everyone kind of jumps on this train. So first of all, they are computationally homogeneous, so it means that they're highly portable. You can take a network, train it on one GPU, put it into another GPU, and supposed to work the same, as opposed to developing all those components where hardware is kind of a little bit different always. It's simple to bake into silicon if you have kind of nice GPUs and so on. Another thing is really predictable runtime and memory use for robotics. So there are like no surprises because algorithm just like a feed forward and nothing can diverge. It's very agile development because people just need to develop this one single module, and people like a researcher would know like the whole system end to end. So as opposed to be a specific expert in SLAM or motion planning, you can be expert in the whole self-driving system. But the main thing is what we're betting on is a superior performance. So we just hope it's going to outperform human coders that code up these self-driving systems. And this is one of our demos. So this is driving in central London, uses cameras only, doesn't use any HD maps or anything like that. So yeah, this is somewhere around King's Cross. Actually, you can go there and maybe catch one. So, and several cool things that started to emerge from that is exactly this emergent behavior that you can observe in other neural networks, large neural networks. So for example, at the bottom you can see that the car on the bottom left, car kind of ignores the paper, a newspaper on the road, while a regular system you distinguish, okay, that's a paper, I can drive around it. But at the same time it avoids bins tipped over on the right. So you can see it just kind of swerves to the right a little bit and negotiates all those, you see here on the right top it waits for a truck to pass by, and we didn't label any of that, it just literally learns from human demonstrations and some other techniques. So this is just emergent behavior. We kind of didn't expect those specific instances. We knew that it's going to perform well, right? But there are several limitations to this approach. Maybe 2.0. The first is that we kind of don't know what's inside this black box. We train those predictions end to end, and explainability and debugging is less straightforward in such systems as opposed to component-based systems. So we just kind of put all this multi-camera, multi-step input and all those inputs in the big transformer and just generates trajectories, so it's hard to say what it does inside. This approach needs a lot of data, as we all know, but here, for that specific task, you need a lot of really weird data, so specifically different combinations of objects, and for every this weird edge case, like on right, you can see a car reflects, and the whole road reflects in the car, in the truck in front, and all sorts of different weird objects on the road, like these people dressed up as cones and so on. So if you want to train such network, you kind of want to collect all this edge case data on actual roads from actual cameras, and it's very expensive to do. Then if you just go with this naive feed-forward network approach, then you kind of don't know how to do exactly planning and prediction. So, for example, if you start to do Monte Carlo tree search, anything like that, it just doesn't scale quite well on board. And the feed-forward network scale poorly with respect to input and output temporal length, because we're just feeding actually camera data. So in multi-camera, so we have multiple cameras. So every new kind of second, you have to feed a lot of data in such systems. It's not clear how to add memory to such systems, how to add common sense reasoning, and how to do hierarchical planning, and so on. This is a given in regular self-driving. And the idea is to solve all of that with multimodal learning of foundational models. So specifically, that's what I'm going to present, explainability we can solve with grounded language interactions with the user. We can use these large pre-trained models that are pre-trained on internet scale data to deal with these common sense edge cases, because they would know, like, okay, well, this is a giraffe, even though we in London never seen it, such a model will recognize it. And in terms of planning, we can do reasoning in language space, like recent chain of thought and so on. You guys know that those GPTs are, pretty okay reasoning through different problems. So we would hope that they can do the same in autonomous driving. And what we did, we started with this is the model that we call Lingo 1. We started with video question answering in self-driving. So this is the first step, where we feed a video from a single camera. We put it into a big model, and it's supposed to produce a text, and the user can chat with such a model. So here are the few challenges right away for that. First of all, it's a vision model, and the majority of research is done with pure language models. So adding vision is a big thing. The next thing is that the video model. So it means that it's not just a model that handles one image. You need to input a cohesive video, and the model should be able to take advantage of the temporal interactions inside that input. And again, majority of research would be in chat models, where you chat about one single image. So then navigation is highly spatial task, as opposed to typically VLMs are trained on like semantic chatting tasks and so on. So here you want to really understand the space around you. Then the next challenge is that there are no actually benchmarks to benchmarks such thing in self-driving. And then well-performing visual language models are probably more than 100 billion parameters, which is GPT-4 and so on, and cloud. But we want to do it on a smaller model. Our first this kind of approach, we started with the BLIP2 architecture, and here specifically the slide trying to address, okay, how to even put in video. This is about this work is about 1 year old already, but there are probably new ways to do that. But here we're just investigating different ways how do you merge video, and you can put it through, one Q-former, generates multiple tokens for the single frame, then merge them, or generate the same set of tokens for the whole video, or mix them in different ways, and so on. And well, I guess we found that obviously the more information you put into model, the better. Specifically here we found that, okay, if you take one single frame, you tokenize it, pass it through Blip Q-former, which is like pre-trained visual language bridge, and then pass it into big pre-trained LLM, you get a better response, which is on the right. I'll show you the responses a bit later. And we train it on all sorts of data sets. Obviously, data sets is the big, the biggest deal kind of in training such networks. And here we want that network to behave well in self-driving, so we took advantage of all sorts of data, academic data sets, and so on. But the main thing, the main amount of work we did was we put into auto-labeling pipelines, where we took our London data and using all sorts of short annotations and inputs from the people, rephrase it with another LLM, and generated a lot of small video QA samples, where for a small video snippet you ask several questions and you get several answers. And we generated tons of such data and kind of trained the model. And the recipe of pre-training is to first merge modalities, and then later you can start fine-tuning the whole thing on your own task. So it was really important to first pre-train such VLM on generic video image data sets, and only then fine-tune it on your own self-driving, our own self-driving BKA task. We tried it just fine-tune right away, and the results were not so good. So it's very important. It's like yet another level of pre-training, right? So because we use already pre-trained LLM, pre-trained vision encoder, so we need to do yet another layer of pre-training to make it work. And here's a small demo that we have on our websites. So if you guys don't see that, what's the weather like? It's rainy. Do you drive differently during rain? Yes, I need to be more cautious due to rainy conditions. Due to rainy conditions, the road might be slippery and visibility might be reduced. When will you go? I will go once the black sedan in front starts moving. When will it stop raining? I cannot predict when it will stop raining. Is it true that it always rains in London? No, it's not true. You guys know. And just to prove that model correct, here's a sunny one. Why is stopped? I'm stopped because the traffic light is red. What are top 3 hazards are you paying attention to? The top 3 hazards are traffic light, cyclists in front of me, and pedestrians crossing the road. Why? I'm paying attention to this hazard because they can impact safety. When can you go? I can go when the traffic light turns green. So you can see that the model, the model correctly pays attention to the important things in driving, which is objects in front of you. It knows which traffic light to pay attention to, and so on. So the next chapter is that it was very hard to evaluate such models because effectively the single thing that truly works is to actually chat with a model and see, okay, does it behave more or less well or not, right? So you cannot really easily come up with an automatic metrics. So for example, if you look at this dialogue on the right, just kind of free-form video questions. You can ask why you stopped, and I'm stopped because the traffic light is red. and so on. If you just evaluate those models with all the employees you have in your company, right? It's still well, first of all, it's quite expensive, but also it's not as fast as you want it to be. Because as a scientist, you want to iterate on like multiple, as I showed, video fusion, ways to do that, different LLMs, different data sets, and so on. And there are some metrics in a space, in a language space, which are called CIDR, BLEU, and so on, which are n-gram-based metrics, which are very fast, but yeah, we found them not to be very robust. Yeah, and yet another way, which is to use GPT-4 or such a very powerful model to kind of evaluate those responses, right? So, what we came up with, which actually worked out pretty well, is to train our own small LLM. In this case, it was based on the BMVA. Just fine-tune it with LoRa and use that LLM as a judge, as an LLM judge. And the architecture for evaluation here is the following. You take this video K model, which is this lingo model, predict some answer, and you have certain evaluation data sets where you have just kind of, I forgot how many, we have like 1,000 questions and answers. And we have a reference human answer and the reference from the model, and the judges need to output 0 to 1 correctness score. And we use yet another data set to fine-tune this model, and then evaluate that on answers of interest of the lingo model. It's just like one LLM fine-tuned on responses of humans and other LLMs to judge yet another LLM, VLM. It's pretty kind of complicated scheme, but I'll show you that it worked quite well. One trick that we found to be extremely useful is to use, well, I mean, the problem that you want to deal with is that when VLM answers on a question, there are actually many correct answers, right? When even in the example, where do you pay attention to, you can say, yeah, I'm paying attention to cyclists and traffic light, and then, okay, do you want to include pedestrians, line kind of ambiguous, and so on. So we found that we need to actually collect more than one diverse answers from humans on the video clip, and then just take a max on several answers. So effectively, we feed several possible answers to the judge. One answer, then a language model answer, another human answer, then the same language model answer, measure all the scores and take the max. It's effectively just, it's kind of more optimistic in a sense, but we deal with this ambiguity. So for example, in this specific case, yeah, there are like very diverse human answers and only one is more close to VLM, and we still count it as being correct. And what we can do next is that we can take different models. Let's say we can take different models that we trained with different architectures, bad ones, good ones, evaluate them using human judgment on the same data set, and then use judge, already pre-trained judge to evaluate the same models, and then build a curve like a correlation and find out correlation coefficients between judgments of human and the small language model, and we get pretty good results. So here the correlation coefficients, we get like 99 coefficients, Pearson Spearman, and we get the same very good results with GPT-4 with chain of thought reasoning. So for evaluation, right? It means that you ask GPT-4 to judge the answers, then you several times recheck that, and so on and so on, and only that leads to like pretty good, the same, well, pretty much the same performance with very correlating with the human very well. But the problem is that if you do that with GPT, it takes 3,000 seconds for our validation set to evaluate, whereas with a small language model it takes only 10 seconds, which means, which is like qualitative gap, right? Because it means that you can run it during training, as opposed to do the experiment and then wait for hours to evaluate something. You actually can plot training curves exactly on the metric that you care about, as opposed to just training loss, which is obviously also important, but here you're literally plotting how it goes. Hence, you can stop the non-promising experiments and stuff like this, which is a very fast development. We have released some of the data that we auto-labeled in the paper, which is available on archive on our GitHub. So it's pretty a lot of video key payers for self-driving. It's about like 300, 400,000 pairs. And also we released the pre-trained judge and 1,000 hand-labeled with humans with KA pairs that you can evaluate your models on. Yeah, and by the way, we also released one simple model that was not trained, that was just kind of for community, and we got pretty good results with that. So this is you can pay attention really to the left column really here, which is a human, is related as a with humans, all those models. And so first of all, we can see that so when humans answer questions and are evaluated by other humans, we get only 93%, which is, there are several explanations to that. First of all, some ambiguity of this video KA, but then noisy humans, like noisy answers, noisy evaluators. And the next best model, being ours, gets only 57%, which means that there is a huge gap between humans and such video models. And the GPT-4V is impressive because it does it zero shot. Our one is fine-tuned on self-driving. GPT-4V does it, just zero shot, but still gets only about 60%, which means that there's huge room to grow for all these zero shot, all these vision models. Note that while we're competing with GPT-4 here, we are only 7 billion model, the one that I presented in here, where GPT-4V is probably, I don't know, 1 trillion or something. There are many rumors. So we got pretty good results. And now going to trustworthiness, explainability. So here's the question: when do we even trust humans to drive a car? And if you think about it, we actually just require humans to pass one theory test and one practice 1 hour test, and that's it. Which is, when I was thinking about this, I was really blown away actually by this, because we as self-driving company test our cars on just magnitudes more of 1 hour practice test, right? We just test the cars in different conditions, different tracks, and so on and so on. And as a theory test, there are some people on YouTube just actually putting GPT-4V to pass UK driving test, and it does pretty okay. So it means that we right now already have these models that we theoretically supposed to trust, but we kind of no one does it, right? So no one yet completely trusts Waymo and other companies, and ours as well, to drive the cars everywhere. So when you think about it, there are several more components why our society can trust humans to drive a car only after 2 hours of testing, roughly. So first of all, we all share the same common sense knowledge. For example, we don't allow kids to drive because we want humans to kind of accumulate till the age, whatever, 16, 17, right? Some common sense stuff, and only then we allow them to go on. But we can do that with a lot of pre-trained VLMs right now, kind of. Next, we know that humans actually can explain decisions. So during the practice test, you can speak with a person, and you kind of get this trust that like, okay, human does something and explains it back. But we can see, okay, this Lingo 1 can explain its decisions more or less, but then we get this backseat driver problem where, you know, okay, it explains the videos, but the driving is done by a different model. So it's kind of this backseat explanation, which is not quite convincing. So then, but the main thing I thought is very interesting is that humans actually use language in this closed loop embodied way, where it's not that we just explain what we do. We first of all learn from the language, so it kind of it feeds back to the motion control and so on and so on. We can reason act in a loop, right? We know that it's all connected together. Our body, the way we behave, and the language. That's why you can trust those explanations. So hence we embarked on the second kind of journey with this Lingo, and the Lingo 2 is an embodied visual language model for self-driving, which we released. We did like 1 week ago, and it's kind of a merge of two models, which is one is Wave's driving model that drives a car, and the second one is Lingo 1, which I just showed. Can answer video QA, and well, after we merge, you get a model that takes in multi-camera, multi-video, multi-timestamp video input, takes in text, can produce text back, and also can generate motion control for the car. So the challenges of that model is that, well, first of all, you get all the challenges of the first model, but then we pretty much have to extend it to multi-camera input, which is a must for driving, because you cannot drive from just... Yeah, the previous model was just a single video feed, by the way. Then the second one is that it's not that we want a small VLM, we want such one that we can run on board in real time, so it controls the car. So we cannot just go with any huge models. And then we get to multimodal training, because now we'll have 3 modalities to train and evaluate, and the majority of papers are dealing with at most 2 modalities, which is language and vision. So here's a more precise slide. So we have a 3 modality being 1 video, 1 text, and 1 on trajectories or actions, because we experimented with different ways to do that. So when you have 3 modalities, you have this problem that you need to pretty much you're never going to have a data set, kind of unlikely to have, where you have all 3 modalities present. So you'll have a data set with 2 modalities, another data set with another 2 modalities, then maybe a little bit of mix of them, and so on and so on. So it's like a big challenge how to merge them together. And this is roughly a high-level way how we did that. I don't want to go into like a lot of details here. But first, we get this Wave Vision model, which is not a clip or anything like that. It's our own self-driving model that we pre-train on a lot of proprietary self-driving data with multi-camera, multi-input. Then we have to do language alignment, where we take this vision model, text data, and so on, and pre-train it to merge video modality and text. And later we need to add the 3rd modality, which is motion control, where we pre-train all of that together. Okay, so here, this is the demo video. It's the first ever LLM, to my knowledge, that can drive a car end-to-end. It should be VLM. So you can, yeah, that's right. You can see the explanations, the text explanation on the bottom. So it just in a mode of explaining decisions, turning right to follow the route, keeping to the left, turning left to follow the route, increasing speed to meet the speed limit, increasing speed, keeping the same speed, road is clear. Kind of nothing happens, so the explanation doesn't change. Just on some scenery. Yes, here's the Big Bang picture. Reducing speed, turning right to follow the route. changing lanes, slowing down to lead the lead vehicle, keeping pace with the lead vehicle, and so on. Okay, so we are merging 3 modalities, right? So it means that there are actually several different modes, because we can kind of drop down some modalities and get different interesting features. So first is just the pure driving, where you just get rid of this text and so on, and you just generate driving from videos. Kind of show. The second one is explaining post factum your actions, where, because we can take actions as an input as well, right? We can take video and actions and generate those explanations, which is very nice for debugging. Another one is to start having this hierarchical control, because you can think about the language decision as a big, like, high-level decision, which then in turn conditions through just causal mask and low-level decision changes accordingly. If you decide something else, supposed to change it. You can add justification here. You can say, okay, I'm deciding, but also I want to explain, which is like a mixture of things before. And here's just one example. This is in our simulator, which is a neural simulator, where you can kind of start to test counterfactuals. So I'm just going to read the bottom. So first, in the video on the left top, it says the moment car appears, kind of stops for the car and says, yeah, I'm stopping for the car. And the second one says, yeah, it's all clear and it's fine. The same goes on for pedestrians on the right. Next, you can do video question answering, because now you can input the question. So here, just to read, we asked kind of the same question on the first 3, what's the weather like, and it generates different correct response, whether it's sunny and so on. And on the bottom, we ask about hazards, and it says it's a cyclist and so on. The last cool thing we can do is that instead of generating question, we can actually generate a command. In that sense, action is going to be conditioned on a human saying something. So here, again, this is a test in a simulator where we take the same condition and just say, generate, okay, turning left, you're going to be stopped, turning right. And the last one, which is kind of future work, we don't have a demo, well, we're working internally, but we haven't released that yet, is that you can start to put chain of thought reasoning into language space, which is then conditions the action. So you can say, okay, so traffic light is green, hence I can go, so the road curves left, and you have some more decisions about buses and so on, and hence my action, and so on and so on. You can kind of go on in the language space, and then you generate finally the final trajectory, which is exactly the planning that I was alluding to at the beginning. Right, so the conclusions is that those multimodal language models close remaining gaps in this AV 2.0 paradigm, covering reasoning, explainability, edge cases, and so on. And in this case of driving exam, again, I think this grounded visual language models that behave in a loop is this missing component for trustworthiness, so that we can trust the AI models, because in that case we would know they live in the same world, they behave the same way, and so on. Yeah, and then it's pretty surprising for me personally that we can even run visual language model on board and control a car in real time. I wouldn't guess so when we got like ChatGPT 175 billion model 1 year ago. Right, that's it. Thank you.
Questions?
Yeah.
Thanks for the last talk. I have a question about the data. So you mentioned all those edge cases, right? So I'm wondering, are you trying to train the model on some synthetic data, like generated from AI, also built by web?
Yeah.
Are you trying to do something like that? I mean, if that is the future. That was the biggest challenge in your point of view.
So yes, in this project we are generating edge case data from our world models, which I didn't present here, and so on, and from simulation. But here it's like what I wanted to kind of to address here is that we as a small startup can make use of this internet scale data by reusing already pre-trained VLMs. So this is the main kind of novel idea that I wouldn't think existed before, because before we were thinking, okay, you can just kind of keep collecting data, maybe in simulation and so on, and you just kind of get it. You can improve your performance, but now suddenly we can say, okay, well, there is an open source model which was trained on all sorts of internet scale data, like let's say giraffes, right? And so that's why when we get it and kind of fine tune it in our data, we suddenly get this knowledge about giraffes, right? Which such that we don't have to generate it in Gaia or generate models or in simulation. So this is the promise, right? We kind of working towards this such that we can actually showcase that, okay, we can generate a behavior based on edge case that was not at all present in our data, right? Such as like some kind of weird animal that we know doesn't exist in our simulations. So we hope for that kind of emergence at some point for edge cases specifically. Yeah.
You can go first.
Okay, thanks. I think it's a great talk. I have some questions. So when you evaluate your driving system, have you tried dealing with some challenging scenarios? I think you mentioned that you tested different weathers, different road conditions, but what if there is a kind of like emergency happens ahead? Can this system still work well on like changing the road? Or have you considered utilizing some GPS navigation system? Because normally for human driving, I like the idea that you compare agent to the human driving test, but also I think most of drivers here will using the GPS navigation, which will give you some instruction to drive more safe. So this is kind of like heuristic, right?
Yeah, thanks. This is a great question. It's not even. It's like bigger than the whole talk about VLMs and LLMs, right? It's how do you test self-driving cars in general, right? And I alluded to that a little bit. That okay, self-driving companies have the whole big pipeline of how to test that, and we would test that model exactly the same way, as robust as we would test any driving model we have, right? The fact that it has language, it's kind of a bonus. We're not going to compromise any. We're not going to say, okay, now we just because it has common sense reasoning, we think it might not do some tests. So. There are so many, I don't know, I can kind of go on for many minutes, like how do you test self-driving cars in general, right? But in general, it's like many, many hours of testing in all sorts of conditions with humans in simulation. You have like different types of simulation. You have open loop testing, closed loop testing, and so on and so on. So it's not even related to, in a sense, like the fact that you have a language in that system.
So I have a second question. So one thing I noticed that most of the test scenario are actually in London, right? So have you think about adapting your model to different countries? One problem issue I can say is that the highway code might change and driving habits may change.
Yeah.
So is this a possibility that you can integrate LLM to read some regulations from existing official documents?
Yeah, exactly. So this is one of the things I didn't address in that thing, but we're just exploring different countries and different cities. On the blog, on our blog, I think we have released the fact that we're exploring in different cities, at least, right? And different countries. I'm not sure it's there. But this is one of the promises. Yeah, I mean, we haven't tested it yet here with the VLMs.
Thank you for a great talk. So my question is, have you tried to use more than 3 modalities, or have you tried to use some other data, for example, LiDAR, radar in your system?
Yeah, not yet. Not in this talk. Not in this model yet. I mean, there are some other modalities being again much anything in a you know, and on top of cameras, like it's all the data pretty much you have in the car, which is, you know, steering wheel and so on, which you can think about as yet another, you know, more in three modalities, right? We haven't investigated yet, let's say, sound, right? You can think about like, okay, if emergency vehicle approaches from the back, you don't even see it as a person, you would like hear it and slow down.
Thank you for the brilliant talk. So I'm more interested in two ways about the model here. The first one is the inference speed of the model, because doing the forward pass takes a lot of time, and how to deal with some cases where the just as the girl mentioned, like when the emergency occurs, is there any specific like numbers about the inference speed, or how long time does it take to do a forward pass, or etc. So that's the first one I'm interested in. And the second one is that could you please explain a bit more about how you actually do the grounding in the model, because it seems that in the example you showed, the model performs quite good in recognizing the actions or the physical environments. But the language model has been long criticized for its lack of grounding in real world, because it is only trained on text-only corpus.
Yeah.
So do you think this is brought by fusing different kinds of modalities, and then the language model could have these capabilities, or are there any more tricks?
Yeah, so on the first one, I cannot tell you the numbers, unfortunately, but I can just say that, okay, if you know self-driving field, right, then other companies roughly run cars, you have to run them more than like 10, 5 hertz kind of thing, right? So in a closed loop, otherwise performance would be terrible. So that's kind of the ballpark, right? So, but this is common knowledge. I cannot tell you like what's the exact latency. So on the second one, this is a research project, right? In terms of grounding, we are trying to like read all the papers, what people do, right? And then this is the hope that you merge more modality and it becomes more and more, again, trustworthy and as a human, right? So specifically addressing that, okay, well, language models have this gap, and we found when we started working on this first version video of language models, we found right away LLMs just are miserable in terms of like spatial stuff, right? So you say things, I'm in front of car, and sentence back, the model just forgets that what does it mean even to be in front. If you do, let's say, my car is faster than the car in front, then GPT-4V even tries to derive, as like a school example, whether I'm going to collide, but makes mistakes there, cannot even have a very common sense reasoning on spatial stuff. So it's actually, I think this is the biggest deal, the spatial reasoning right now, right? So whatever, any way we can deal with that, which is would be vision, but then another thing, even with vision, with all the VLMs, they're just not focused on spatial queries right now, right? So they just say, okay, this person may be on the left of that person in the picture, but we found that, let's say, GPT-4V cannot even correctly say if you put several frames, you cannot say if car goes forward or backward. You cannot distinguish between them because they're not focused on this cohesive videos. So actually, spatial dimension is a big thing, which is what we're trying to cover with data, obviously, right? I mean, because we have all sorts of spatial data as a self-driving company. I don't know if it answers some of them.
Why do you have two different stages for vision pre-training and then alignment? Why can't you do
I don't know why. Yeah, no. It's the same as why instruction fine-tuning follows general pre-training, right? Humanity found it to be working. Yeah. So similar thing, right? I mean, we can pretty much say that. Hypothesis would be that you typically have way less instruction data, right, or any label data, and this initial pre-training just like sees so much data that somehow puts into like nice mode for later fine-tuning. So because yeah, this is like a common thing, but this is a hypothesis. I don't know, like if people tested that.
Limited by the time, let's have offline discussion. Yeah.
Perhaps a last question, quick one?
Yeah.
Right, great. Great talk and very good work on the Gaia and the Limbo 1 and 2. Congratulations on that. I can remember that as Alexander first released that last year, Jan LeCun had retweeted basically that message, says, okay, it's a word model. So my question is exactly related to that. So basically, is that a really word model, or is it just a kind of a statistical parrot?
So yeah, this is, I can actually go on for a lot, arguing with LeCun. This is like, I'm going with my head like quite a lot.
Right. No,
So yeah, so I don't think, so on statistical parrot, right, first of all, I think that humans are statistical parrots.
all right.
So hence we just like happen to be way better than parrots at repeating words, right? But I mean, I'm right now have no idea what I'm going to say. I'm just generating it in I don't have a plan what my sentence is going to be right now, which is just happened, right? And you yourself, if you think about it and start thinking like how do you generate sentences, it just kind of comes out, right? The same with your thoughts. They don't come from some kind of deeper planning that LeCun kind of always alludes to. So I think we all just autoregressive models, right? Maybe with a little bit more levels. Obviously, I'm not saying that we're totally like one level LLMs, right? But it's more complicated a little bit than that. So hence, the answer to your question is yes. This model is statistical parrot, and yes, it can do everything else. And humans are also statistical parrot. Right?
Let's thank Dr. Oleg. And now we have 15 minutes for the coffee break and the check for the poster during the neighbor.